All right, let's find the binding energy and the binding energy per nucleon of fluorine-19. This is the reference, so you'll get to use this isotopic mass table. Yes, there we go. This is in your data packet. I will put this on the test, okay, but we don't need that. It's actually in that isotopic mass packet. But I just put it there because there it is, right? Okay. Now, remember, the first step here is you got to figure out, fluorine means it has 9 protons. If it's got 19 total protons and neutrons, our first step is that this thing is made of 9 protons plus 10 neutrons, right? Okay. And it also has 10 electrons, or sorry, 9 electrons. Okay. But we take care of the protons and electrons by using the mass of the neutral hydrogen atom. This is 1 proton, 1 electron, literally. Okay. So we're going to compare the mass of this guy, which is 18.998403. Okay, we're going to compare that to the mass of 9 protons and electrons, right? So 1.007825. That's the neutral atom mass of a hydrogen atom, right? And then plus 10 protons, right? So 10 of these guys, right? 1.008665. Okay, so let's figure out this left side there. 9 times 1.007825 plus 10 times 1.008665. I would memorize these guys, but it's not required. I'm just saying. Okay, and you'll see. Whoa, wow, it's juicy. 19.157. Holy mass defect, Batman. 0.75. Right, the parts have more mass than the atom put together. So if you go this way, if you make the atom, where does that mass go? It turns into energy. Right, energy is released in the making of this. By the way, in chemistry, you do a very similar thing in PChem. There's energy of formation, and you'll look up the energy of formation of compounds. And yeah, that's all I remember. All right, so we're going to do some subtraction here. So I'm going to subtract this from this and figure out how much mass was gained in tearing this thing apart. Okay, so minus 18.998403. Did I do that right? I did that right. Holy cow. So the change in mass is, by the way, almost everything in this entire test is the same theme, right? You're going to find 2 different masses by looking things up in the table, okay? And you're going to, this is probably even harder than nuclear reactions. You just look the things up, look at the mass difference. That's the energy. Okay, so this is our mass difference, and each one of these if you create it from pure energy, this mass from pure energy, it represents that much energy. So we're going to go times 931.5 MeV per U. And they like to say per the speed of light squared, which I find strange, but I've never seen that, but maybe, I see what they're doing, but okay, so I'm going to go times 931.5, and this is, wow, it's 147.802968. Now, this thing is the only thing limiting us. We really have 1, 2, 3, 4, 5, 6 sig figs. This has 4 sig figs. So really, we can only justify 4 of these things. Now, if you could look up a better value of this, and for sure it exists somewhere, right? Just Google it. You could have 6 sig figs, right? We could be all the way down to here. But at this point, our knowledge ends at this decimal point, 1, 2, 3, 4 sig figs, right? So we would say 147.8 MeV. And I've seen this, I think on the packet you're going to do, they do ask you, how many sig figs would you have? And anyway, got to get the number right. Okay, so there it is, right? Now, per nucleon, right? How many nucleons are there? Well, that's what the 19 is, right? They're telling you it's fluorine with 19 total nucleons, right? Okay, so we're going to divide that by 19. So on my calculator, divided by 19, it's 7.779 MeV per nucleon. Nucleons being the set whose members are protons and neutrons. All right.